let's wait for a minute for everyone to join. Let me state it again. The quiz tonight and starting this evening at 6 p.m., which will be available until tomorrow 6 p.m., is going to be about chapter 3. And I think it's going to specifically be about Poisson random variables. And now we're going to start chapter 4, and we'll see some continuous distributions and some discussions about those. All right, so yeah, I'm recording. Let me enable scrolling here too. So continuous random variables, as I said, we already discussed some of these when we talk about random variables in general. It may assume a continuous random variable may assume a real value in an interval. It may be bounded, but still uncountably infinite, like it may be in a fixed interval between a and b, but it may have any real values. It may be a real value random variable in this interval. It may be unbounded on one left hand side. It may be unbounded on both sides. So, and some examples are when you measure time until next event or time between two events, when you're measuring time, that's, for example, bounded at 0 and goes all the way to infinity. You may measure temperature, which may be bounded practically. For example, the negative temperatures cannot be smaller than 0 Kelvin, but theoretically they can go as high as they can. So it may be bounded by one side, unbounded on the other. When you're measuring length, again, it starts at 0, goes all the way to infinity. Weight, similarly. Some of them are non-negative, but some measures can be negative. But if you're measuring something which can take some real values, then we may treat it as a continuous random variable. And we also talked about this when we are talking about continuous random variables. Point events have 0 probabilities. I remember last week we were discussing how these two terms PMF and PDF, do they have the same meaning? Are we going to have PDFs for the discrete random variables? Actually, probability mass function here is a terminology used to specify point probabilities. So in other words, the probability mass function, PMFs, of continuous random variables is always 0. It's like we cannot look at point probabilities. So instead they have PDFs. So when we have this probability density function, which is a derivative of the cumulative distribution function, we will solve intervals by computing the area under the probability density function. Usually when we are asked probabilities, in the case of continuous variables, we will never be asked to compute the probability of some continuous variable to be exactly equal to x. This will always be 0. We will be asked probabilities like, what is the probability that x is between c and d? And in the case of if x is continuous, it doesn't matter whether this is an inequality or equal, less than or equal to, okay? Whether there's an equality involved in this or not will not make a difference, because x is equal to d is 0. So when you're computing the area under the curve, whether the boundaries are included or excluded doesn't make any difference, because the length of those, the areas of edges, the area of a single edge is 0. It is just a line segment, it's a line. It has 0 area. It means that whether you have the equality symbol here or not doesn't matter in case of continuous random variables. In case of discrete variables, it's of utmost importance. Whether it's equal or not, that this changes probabilities in discrete random variables. Okay, so so this is basically Whether you have equality or not doesn't matter in case of continuous random variables. And the cumulative distribution function, the cumulative distribution has the same meaning as in the discrete case. It means that the probability probability of random variable x is less than this given x. And in the case of continuous, these two are equal. We have talked about this. Unlike the discrete cumulative distribution functions, continuous CDFs do not have jumps. They do not have immediate jumps. Therefore, since the point-like probabilities are zero, so we cannot have an immediate jump at a point. Therefore, they are continuous. Cumulative distribution functions of continuous random variables are continuous functions like this. They start at 0, and it's a non-decreasing function that will reach 1 at some point. Okay, so this is what you see here is a random variable which is defined starting at 1 and going all the way to infinity. For example, this was, I think, from an example in the book. It is, we can take a look at this PDF. So yeah, it's this one. So if you look at this, it's this example. The PDF is given to us as k over x cubed for values of this random variable greater than or equal to 1. For less than 1, it's all 0. So this random variable is defined 1 and onwards going to infinity. If this is the PDF, what is k? So k is not specified here in this question. Find what k is. What we need to do is, in order for this to be a valid probability density function, the area under the curve, the total area under the curve has to be equal to 1. So when we integrate this from 1 to infinity, k over x cubed, if we integrate this function k over x cubed from 1 to infinity, that's our total probability of the sample space, which should be equal to 1. And if we set this integral, we turn this, when we compute this definite integral, we get ourselves k over 2. K over 2 is equal to 1, which means that k should be 2. So in order for this to be a probability density function, and you define a function like this, it should be 2 over x cubed. That's your probability density function. And this becomes the cumulative distribution function from, if you integrate to 1 to x, when x is not given here, it's not infinity, for a given x, the cumulative distribution function will be the integral from 1 to x, and this becomes that cumulative distribution function. Now we can compute probabilities like if this function was the lifetime of a electronic component, we can ask probabilities like what is the probability that the lifetime of this component is going to be greater than 5? And then what we need to do is we need to find what is the probability that it's going to be less than 5. So we will integrate from 1 to 5, and this we are going to find f1. And then if 1 to 5 is like 0.96, the probability that the lifetime is going to be more than 5 years is going to be this small probability of 0.04. So this is just an arbitrary, this is not a family of distributions, okay? So this is just an arbitrary function that is given to us as the probability density of a continuous random variable, but we can still use this to compute integrals and therefore to compute probabilities of intervals that are given to us. So this table shows the relationship between discrete and continuous random variables. So whenever we ever summing things, the summation symbol is turned to integrating over an area, over an event. So if the probability that x is this event, A is a subset of the sample space. So A denotes an event here. The probability of this event is we sum over all outcomes that belong to this event, and we sum those probabilities. Similar to that, we sum over the area that is indicated by this event. This area may be disjoint. In that case, we need to compute and sum up those disjoint areas. So this is the CDF definition. This is the total probability is this. So these are the relationship between PMF and PDF. And similarly, when we talk about joint and marginal densities, the joint cumulative distribution function means that, for example, the probability that these two random variables x and y, when we are given these two parameters in the joint joint cumulative distribution function xy, it means that the probability that x is less than or equal to x and the probability that y is equal to less than or equal to this small y. So this is what the joint probability means. And this will be equal to the multiplication of the individual marginal probabilities if only they are independent. If they are not independent, we have to find these probabilities. For example, if this is given to us, it will be an arbitrary surface, and it will not be a multiplication of individual probabilities, and therefore we need to use double derivation or double integrals in order to compute probabilities. So this is all the summations, summing over an entire single variable to find marginal probabilities. It's the same idea, just change it to integration over, for example, if you want to find the marginal probability of y, you have to integrate over all possible values of x. Okay, so even if we have this two-dimensional function with two parameters, if you sum over the all possible values of x, you're going to get the probability of the individual marginal probability density function for y. So all these things, as I said, are discrete and continuous cases are analogous. Summations are turned to integrals, and everything else remains the same actually. But the independence and computing probabilities all will be very similar. And here's what the expected value means. We now have a continuous variable. You may still think about this as the center of mass of this entire function. This is the probability density function. If you think about this as a uniform made up of some uniform material like wood, the expected value will be like the center of mass point of this distribution. All right. Do you have any questions? Okay. The variance is computed similarly. The formula is the same, the variance formula. As I said, the summations are turned to integrals, and the covariance, everything is just analogous to the discrete case. So I'm skipping these parts. So let me go back to my slides. So given the cumulative distribution function, the probability density function is defined as this derivative of the cumulative distribution function with x. So this is actually a description of, the same repetition of the same thing that we have went over in the book. So this is the same example in the book. What is k? Find the CDF. What is the probability for the lifetime to exceed 5 years? We have went over this in the book. So I'm skipping these parts. If two events are independent, the two random variables, not events, sorry. If two random variables are independent, then their joint probability density function is a multiplication of those. But if they're not independent, we cannot just multiply them like this to find the joint distribution. Expectation, variance. So yeah, look at this. Compute the expectation and variance. If fxx is this, if this is the PDF for x greater than 1, compute the, let's try to do that. For example, if 2 times x to the power minus 3. So this is, if we are given a PDF, which is this, fx is equal to 2 times x minus 3, like this. What is the expected value? How are we going to, and this is x greater than or equal to 1. How are we going to find the expected value? Expected value will be the integral from 1 to infinity x times this PDF, x minus 3 times dx. So if we compute this integral, you're going to find the expected value. Let's try to do that. What is it? So this multiplied with x, so it's going to be the integral from 1 to infinity 2 times x minus x to the power 2 dx. Do you remember any high school knowledge, or maybe calculus? You have taken calculus, right? And not high school. We shouldn't go that far away. Last year you should have taken calculus courses. So what is the integral of this to x to the minus? So is it 1 over x something, right? Is it going to be 1 over x? It's going to be minus 2, yeah, 1 over x. It's going to be minus 2 over x. Yeah, those 2's are, 2's don't cancel. It's yeah, minus 2 over x from 1 to infinity. Okay, so when you give infinity to x, it's going to be 0. It's going to be 0, and you give, so 0 minus 2. Is it going to be 2? So I think it's going to 0 minus 2. I think it's going to be 2. Let's go ahead and take a look at what we have in the book. It's example 4.2. So when we go ahead and look at example 4.2, it has to be somewhere here. Yeah, it's 2. So its expected value is going to be 2. So we found it correctly like this. What about its variance? What is its variance going to be? So the expected value of random variable with this PDF is 2. When we try to find its variance, what we need to do is first find what is the expected value of x squared, right? We need to find this, which is going to be equal to from 1 to infinity x squared multiplied by that 2x minus 3 dx, which is going to be 1 to infinity 2 x 1 over x. So it's going to be ln x something, right? 1 over infinity 1 to infinity ln x, or 2 times ln x, something like that. But it says 2 times ln x. Thank you. 2 times ln x, and ln, oh, the infinity is not 8. Infinity symbol is right like this. So an ln infinity is infinity. So when you compute the expected value of x squared, it's going to turn out to be infinity, which in turn means that if you subtract from this 2 square, which is the square of the expected value, it's still going to be infinity. So in other words, variance of this is infinite. So we have a continuous random variable with some interesting property, which is its expected value is 2, while its variance is infinite. So let's see, that's the case. Yeah, 2 ln x, yeah, it's exactly like what we have found. So we have infinite variance random variable. All right, so let's continue. Yeah, we are going to now see some important continuous distributions, starting with the uniform distribution, which is the simplest one in some sense, because we are also have functions that give us, it's really simple to simulate, because most of the random variable generators, they give us uniform random variables. And on Octave Online, for example, the function rand give you some random numbers between 0 and 1, uniformly distributed over the interval 0 and 1. So this rand function in Octave Online gives you that. For example, if there's also possible to generate a vector of or array of random numbers, and to do that, you specify the dimensions of your matrix or matrix of random numbers. For example, let's get Octave Online to generate us 10,000. So the second dimension means that it's 10,000 by 1 matrix. So it's a single row or single column of whatever your dimensions are of random numbers. It's just a vector of random numbers. So this is what U is. There's a function named histogram, hist, in Octave Online. If you take a look at the histogram of this, you'll see that all the numbers that we have generated are between 0 and 1, and they are roughly, for example, a little more than 1,000 of them are between 0 and 0.1. A little less than 1,000 of them are between 0.1 and 0.2. But if you look at this, since this is a simulation, it's not exactly a straight line. But if we increase this number, or if you decrease this number, let's generate 100 random numbers and take a look at the histogram. Wow, the histogram also is. Oh, what did I do here? No, histogram view, not 100. So yeah, histogram of 100 is just a single point 100, right? So this is when you generate 100 random numbers. As you can see, this doesn't look like uniform. For example, we were unlucky between 0.7 and 0.8. We get a lot less numbers. But when this is what happens in simulations. If you perform your experiments more and more, you get more and more closer to what it really looks like to be uniform. So let's generate 1 million random numbers, and let's take a look at the histogram of those 1 million numbers. You'll see it looks more like a constant value. We get more and more values between the same histogram bins. Okay, so this is what uniform random variables are. They get us constant density between two intervals. In standard uniform, many of these family of distributions, they will have some standard form. You will see standard uniform, standard normal distribution. When we refer to those standard distributions, it means that these parameters are fixed to some numbers. In standard uniform, A is equal to 0, B is equal to 1. So if somebody asks you that, let me give you a standard uniform number, and they don't need to specify the interval. A standard uniform number is going to always be a real number between 0 and 1. Okay? Similarly, we'll see like standard normal distribution. Standard normal distribution, the mean, two normal distributions will have two parameters, mean and standard deviation, or mean and variance. The mean will be 0 for standard normal, and standard deviation will be 1. So those standard versions of those distributions are used a lot. And if you're given a non-standard version, if you're in your problem, you're trying to solve a non-standard uniform distribution, probably related to some non-standard, you can always convert one to the other. For example, any non-standard uniform distribution is just a scaled and translated version of the standard one. For example, give me any A and B. By the way, the intervals should be in such a way that we cannot have infinity here. Uniform distribution cannot be unbounded, okay? Because we have a constant function, we cannot have an unbounded function so that we have a constant function, because the area under the curve is not going to be equal to 1. So give me any A and B in such a way that B is greater than A. For example, let A be 200, B be 500. Okay, so let me turn on the annotate. So if A is 200 and B is 500, I want to get this pen, not that one. So how can I change the pen? Oh, it's still, am I annotating? Yeah. Pencil tool. Yeah. So if you want to get something between 200 and 500, what is this uniform? It's like the standard uniform, which is between 0 and 1. If this is my random variable x, and this is y is nothing but 200 plus 300 times x, right? It's just a scale. You enlarge your standard distribution 300 times more because the interval between A and B is 300 units long. So you scale, you enlarge it 300 times, and then you move it to 200 so that it's moved on the x-axis to this variable. So any uniform random variable like this y could be generated as a linear combination of the standard uniform random variable x like this. Okay, so in a sense, it's going to be a plus b minus a x. So if x is my uniform random variable, you can generate any non-standard uniform random variable with this. Its expected value is exactly the center of the distribution. So a plus b divided by 2 is the center of the density, probability density function. And its variance, you may compute the variance by integrating, by finding what is the expected value of x squared, again, by trying to find if the fx dx is this one, 1 over b minus a. You multiply this with x squared and take the integral, okay, to find the expected value of x squared, and subtract from it this a plus b squared. If you subtract from that the square of the expected value, you get yourself the variance. Okay, so which is this b minus a squared divided by 12. So you just need to do some mathematics, taking some integrals to do that. All right. An important property of uniform distribution is that by using this uniform distribution, we'll see that we'll be able to generate any arbitrary, we will be able to generate random numbers from an arbitrary distribution, because we'll see that when we come to chapter 5 actually. But one important property is that the inverse function of the CDF. So let me write it here. Why do I always want to get pencil as the default? So if you have some CDF function, which is a non-decreasing function, right? So if this is the CDF of some, wow, I really hate it. Whenever I click somewhere, the annotate immediately disappears. Okay, so maybe I should directly use GIMP. Yeah, let me do that. I don't need to draw it on the slide. Okay, so what I'm saying is that if we have the CDF function, the inverse of this function, if you take a look at this function, as this is the x-axis and this is like the y-axis, if you take a look at the inverse of the CDF function, you'll see that it's always uniform. So in other words, if somebody gives you a uniform random number from here, if you generate, instead of generating these, if you generate a uniform CDF value here and try to figure out then what this y is, and by using this, you generate your random variables, you'll be able to sample actually directly from the original PDF. We are going to come to that. So this is just a very look ahead of what we're going to be doing with uniform distributions. But just at this time, I'm not going to go into details of this, but just know that with uniform random variables, you can generate random variables from arbitrary distributions. If their CDFs are invertible, if the cumulative distribution function is easy to get the inverse, it's really simple. If it's not invertible, if we have a function, an arbitrary function like this, it's still possible. Okay, so there's also a technique, for example. Let's take a look at our arbitrary function. Where was it? Yeah, look at this one. If we have a PDF like this, we'll still be able to generate random variables from this arbitrary distribution by, for example, this technique, which is going to first put the entire distribution in a rectangle like this and generate random points in this rectangle uniformly. So we are going to generate two random variables, let's call them x and y, which are both uniform, and they are going to be, so just generate uniform random points here like this. And all we are going to do is, if this random point is, we are going to evaluate the PDF at that random point fx, okay? And we are going to compare its y coordinate with the value of this fx. If fx is less than y, as in this case, look at this. Look at this xy, the generated random variable. fx at this point, the PDF, is less than the y coordinate of this xy, right? In that case, we are going to reject this sample. We are not going to accept it as a randomly generated point. If it is this, if fx is, in other words, if the generated point is under the curve, if it's this case, we are going to accept it as a randomly generated sample. And guess what? For the parts where the PDF is higher like this, more points are going to be generated in these regions because more points are going to be likely to be under the curve. So we are going to be generating more random points. I mean, if you just imagine you generate uniform random points, all the points are all over the place in this rectangle. And what you're doing is you're accepting the points that are under this curve as your randomly sampled points. And in a sense, you're randomly generating points from that distribution. So here, as you can see, we used uniformly generated numbers to generate random variables from an arbitrary distribution. This, by the way, this technique is called rejection sampling, and we are going to learn about this later. So this is called, there's also importance sampling. So this is rejection sampling. Importance sampling is using actually this function directly to increase the likelihood of generating this sample. I think we're not going to see it in this course, but there are many ways to generate these random variables from arbitrary distributions, but it's very useful. Look at this rejection sampling technique. What if, for example, some physicist comes and says that this is what we observed about uranium, for example, half-life. Uranium, when interacting with different particles or multiple particles when they're interacting with each other, we observed such a different function, mathematical function, and we want to simulate this in the lab to actually simulate what will happen in the long run when we observe this behavior in our samples. And so you have to generate simulations that conform, that is similar to what you have observed. And with uniform random variables like this, you'll be able to generate arbitrary random variables. But this is, as I said, a topic of chapter 5, which we're going to see towards the end of the semester. All right, so uniform also, just like exponential distribution has a memory list property, uniform property indicates that the location of the probability that you're looking for doesn't matter. Since we have a continuous PDF, if these areas A and B are equal, if the areas are equal, it doesn't matter where this A is. You can shift it in any place on the distribution. You will still have the same probability. It's like asking this. For example, if a flight is going to arrive, so this is the example from the book. If a flight is going to arrive between 10:20 and 10:40, for example, the probability that it will arrive between 10:25 and 10:35, let me write it here. Imagine we have a flight arriving at a with uniform probability. We know that it's going to arrive between 10:20 and 10:40 in these 20 minutes. If somebody asks you what is the probability that it's going to arrive between 10:25 and 10:35, this probability is exactly the same as if somebody asks you what is the probability that it's going to arrive in 10:22 and 10:32, or what is the probability that it's going to arrive at between 10:30 and 10:40. Okay, all these probabilities are equal. If that probability is C, this will be C, this will also be C. Okay, actually we know that it's going to be 1/2, right? If it's uniformly distributed between these two variables, it's exactly the half of that interval, 10 minutes. This is like 20 minutes. If it's equally likely uniformly arrive in 20 minutes, this one is saying what is the probability that it's going to arrive in this 10 minutes, or in this 10 minute, or in this 10 minutes. It doesn't matter. They all are 0.5, 0.5, 0.5. So this is called the uniform property. It means that we can shift the probability when it's shifted in the interval that is defined. The probability doesn't change. By the way, if when we're shifting this, if this shifting takes one part outside the interval, outside the domain of this random variable, then this property doesn't hold, right? I mean, if I keep shifting this b, and as soon as this part of this b is outside the area larger than b, since that at that point probability is 0, we will not have the same thing. In other words, if somebody asks me, what is the probability that it will arrive between 1035 and 1045, that's not the same thing, because we are now outside the bounds of 1040. This will be a different probability. From 1040 to 1045 is going to be 0, and therefore here this one is going to be 1/4 or 0.25. These are not the same, going to be the same area intervals. All right, so after uniform is, I talked about standard uniform. When these A and B are 0 and 1, it's called standard uniform distribution. And by default, for example, Octave Online or other random number generators, they give you standard uniform random numbers. When I, by the way, one of your microphones is open. If you have a question, I'll be happy to answer, but if not, I'll be happy to, if you can mute yourself. There's some background noise. So 0.5, 12, 8, as you can see, these are all standard uniform numbers. Oh, we got a 0.99, 1.8. It's a really low probability, right? So I should get myself a lottery ticket. So, but yes, all of them are equally likely. Okay, you can get yourself a lottery ticket if you get a small number too, or 0.6502. It's really rare. All of these numbers are rare. They're all equally rare. All right, so and now the final thing that I'm going to discuss today until 11:30 is exponential distribution. As I said, exponential distribution is related to Poisson. It's the lambda in Poisson, the average number of events in a time interval, has the same meaning. In exponential distribution, we use the same, you're given the same parameter. We, for example, observe 5 accidents in a day in Ankara. That's our lambda. And when we ask, for example, when we are asked about probabilities, what is the waiting time until the next accident? That's the exponential random variable. When we talk about the number of accidents happen tomorrow, that's a Poisson random variable. If you think about the number of accidents, you cannot have 3.5 accidents. You cannot have 2.1 accidents. A number of accidents is an integer number, therefore it's a discrete random variable. Okay, so that's the Poisson random variable. And when we ask what is the probability that we will have more than 10 accidents tomorrow, that's your Poisson random variable. But when we are asked that what is the probability that we have to wait 3 minutes, or what is the probability that there will be an accident in the next, or I will have to wait 10 minutes, one hour until I see an accident, that's your exponential distribution. It's called inter-arrival time, time between two events, time until failure. That's the waiting times are usually modeled as exponential distributions. Okay, and it's a continuous version of the geometric distribution. As if you remember, geometric distribution is the number of trials until first success. So it's the number of the time that elapses until the first event. As I said, it's related to Poisson. They have the same meaning in both distribution. If we visualize rare events here on the time axis like this, if these red dots are your rare events, by the way, we call them rare events because when two events happen at the same time simultaneously, the discussion on exponential distribution like collapses. I mean, we have to have some times. I mean, actually, it doesn't collapse. It's possible to wait 0 minutes between two intervals, but it makes certain things philosophically difficult to comprehend. The reason we call these rare events is that the possibility of observing two events at the same time is very low. Okay, if you're modeling something that occurs in which this probability of observing two things at the same time is very low, such an event is usually labeled as rare events. And like many things in probability and statistics, there is no black and white distinction between rare and non-rare events. It really depends on, the distinction between them is really blurry, okay? So any event, we're not going to talk about non-rare events in this course anyway. So you don't, if you're confused about this, yeah, don't worry about it. So number of events in 1 minute was our Poisson variable with lambda, when the average number of events in a minute is given to us as lambda. If we were asked what is the number of events in 2 minutes, remember this is not a summation of two random variables, but it's going to be another Poisson variable with two lambda this time. The parameter changes. Now, and in general, number of events in t minutes is going to be t times lambda. This is how we find our Poisson random variables. And in this case, time between events are going to be, between any two events are going to be exponential. Time to first event is also the same exponential. So the time between any of these events is an exponential random variable with same lambda. We are going to talk about the generalization of exponential, which is gamma distribution, which is, if you're asking, for example, what is the time until the fifth event or sixth event, when we are not looking at the next success, but the 5 events on what is the time that has to elapse until we observe 5 events. That is like similar to the generalization of geometric to negative binomial, right? If you remember negative binomial, it's k successes, and in order to get k successes, how many trials I have to have. That was negative binomial. If you generalize 1 to k, this is how you move from geometric to negative binomial. Here we'll have the same thing. We'll move from exponential to gamma distribution. The generalization of the single event to multiple events, observing multiple things, will be from exponential to gamma distribution. In addition to lambda, we are also going to have another parameter named alpha this time, which in general can be continuous, not necessarily discrete, as in the case of negative binomial. Okay, but time between events is generally an exponential CDF, and this is the PDF function. We say it can be derived from the Poisson PDF because they're related like this. What is the time to wait until the next event is what is the probability that in this event I observe 0 events. So if you plug in 0 for 0 for your number of events that you observe, then take 1 minus that one. So this is exactly written here. The waiting time. So this is the Poisson PMF, sorry. So this is the Poisson PMF function. The waiting time for the next event is greater than time units. So what is the probability that I will have to wait at least t time units until I observe a single event is the same probability that I observe no event until t. 0 events occur in t time units. So this one is a Poisson random variable. Okay, if we fix this t, if we fix this t, observing 0 events in t time units is the same as saying that you have to wait t times until you observe the first event. So if x is a random variable that shows the number of events in t time, which means that if x is a Poisson random variable with the parameter t times lambda, where lambda is defined as the average number of events in 1 unit. Okay, so for example, if lambda is given to us, the average number of events in 1 minute, and here t is what is the probability to observe in 10 minutes. What is the probability that I will have to wait 10 minutes until the next event is now a Poisson random variable with t times lambda, right? In 10 minutes, I have to multiply my given lambda to t times lambda, which is the average number of events that occur in 10 minutes. And therefore, in order to find the probability that you have to wait at least 10 minutes to observe a single event means that you don't observe any event for that 10 minutes. So it's your PMF function in Poisson, fx0, and this gives us, this is the CDF e to the minus lambda t is our CDF function for exponential. And if you take the integral of that, you get the PDF of exponential function. So this is 1 minus this actually becomes this. So observing no events until that time is our complement event. And by using that, this 1 minus e to the minus lambda t becomes the cumulative distribution function for the exponential CDF. If you take the derivative of this, you get the PDF, which is simpler than this, which is not, it's just similar to the CDF. As you can see, lambda is now to the front. Lambda times e to the minus lambda t becomes our PDF function, and its shape. We can take a look at its shape like this. So let's exponential, and I'm going to end the lecture after that. Exponential PDF. So if you look at some images, and here is one image. The PDF looks like it's a decreasing function like this. This is the probability density function. And as you can see, the lambda, which can be a continuous number, a real valued number, as lambda increases, we get a sharp decrease in the exponential PDF. For smaller lambda, our exponential function is decreasing slowly. Okay, so the PDF, this is the PDF of exponential distribution. It starts at 0 and goes all the way to infinity. All right, so I'm going to continue with gamma distribution and normal distribution on Thursday. I'm going to stop recording now.